Okay, welcome back everyone to these tutorial videos for the Theory of Computation course. In this video, I'm going to be showing you how to design a context-free grammar so that you sort of already have seen a few videos and sort of examples of that by now. But the other thing I'm going to do in this video is I'm also going to show you how to prove that your grammar is correct, okay? Because if you actually truly want to prove that a language L is regular or context-free or whatever, you first have to design the computational model or the grammar that accepts or generates it. And then you have to prove the correctness of that model or of that grammar. And so we haven't been doing a lot of that so far, but it's a good skill to sort of develop, and it's good to know that you do need that extra proof of correctness for your answer to be completely rigorous. So that's what we'll be doing in this video. Okay. So what is the language in this case that I want to for which I want to design a context-free grammar? So in this case, it's going to be the language over the alphabet AB, where the strings in that language contain the same number of A's as B's. Okay. And so notice here, there's no restriction on the order, right? So it can be in any order, right? So for instance, right, so for example, strings in L could be something like AABB, right? Because here I have two A's and here I have two B's. I could also have something like AB, because here I have two A's and here I also have two B's. And I could also have something even wilder, maybe something like BBAA, and then something like ABBA, because here I have four B's and here four A's, right? And so on, right? Okay. So so that's the sort of identity of the language for which I want to construct a context-free grammar. Now, I'm going to use the same principles as I have in previous videos. So I'm going to try to capture the recursive nature of the language and use that nature to develop rules for my context-free grammar. In this case, it's going to be a bit trickier because of what I just said. There's no imposed form on the strings in L. So we're going to have to be a bit more creative. You'll see what that means in a second. Okay. So first of all, what is the base case again in this language? Well, the simplest string that is in the language L, right, has no A's and no B's, right? Because I have zero A's, zero B's, zero is equal to zero, and so that will be in the language L, right? So in this case, again, this is not true in every single example we'll be doing. It's not true that the base case is always epsilon, but in this case, and if in a few other videos, it has been done, right? So, but so again, in this case, it's going to be S gives you epsilon, right? That's going to be my base case, right? So remember, think of the variable as you sort of take it for granted that it allows you to generate strings in the language. And when you develop the recursive case, you sort of want to build upon the strings that S can generate, right? And so that's how you sort of recursively build up longer and longer strings. Okay. So, and so definitely that's why S gives me the empty string should be the base rule, because that's the simplest kind of string that exists in L. Now, what should be the recursive case? Well, if we look at these first two examples of strings in the language L, it looks like what's going on is for every A that I have, right, in my string, I have a corresponding B, right? And that makes sense, right? So that means that I always maintain the equality of numbers and of A's and B's, right? So it's the same thing here, right? So For every A I have a B, and for every B I have an A. So one natural thing that you might want to say is, well, then the recursive case will probably just be S gives me A S B and B S A, right? Because then I can, I can generate a string that looks like this and generate a string that looks like this, right? But that's a bit of a problem, right? Because what this is sort of assuming is it's actually assuming a kind of form of the string. It's assuming that um, for every A there's an opposing B, and for every B there's an opposing A, right? And for instance, it doesn't work in this case, right? Because it'll work for this part of the string, but then I have a B and then a corresponding B, not an A, in the string. But the string is valid, right? It's in the language L. Okay. So that tells me that this is not quite correct. And what it's telling me is that I need to sort of to loosen um, the rules, or maybe add a rule to allow for arbitrary order. Okay. And the way that I'm going to show you how to get to that extra rule. So it turns out we actually just need one more rule to make this grammar correct. Um, but to get to that sort of final rule, I think it's going to be useful to show you another sort of trick that sometimes helps when it comes to designing context-free grammars. So the trick I'm going to use is we're going to use a plot. Okay. So yes, you read and heard correctly. I mean plot as in like a graph where I have a line going up and down. Yeah. So that kind of plot. Now, you might be thinking, well, what do plots have to do with context-free grammars and recursive cases? Well, you'll see in a second. Um, be patient with me. Let me just set this up and show you how I'm going to design a plot. So imagine, right? Imagine that I have some string W in L, right? So what do I know about my string W? I know that it's even, right? It's of even length because I have the number of A's is equal to the number of B's, right? So the length of W is equal to the number of A's plus the number of B's, but these two things are the same. So I can just write this as something like 2 times number of A's, right? And so that tells me that the length of W is even, right? Okay. Why is that helpful? Well, if I want to sort of explicitly represent the string W in terms of sort of sequences of letters, how can I do that? Well, I can just say that W looks like sequences of letters, sigma 1, sigma 2, sigma 3, dot, 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 sigma 2k minus 1, and sigma 2k, right? So where let's consider just k greater or equal to 1, because we've already considered the empty string, right? And where, of course, sigma I is either A or B, right? So I'm allowed to say the sequence of letters that form this arbitrary string W and L are something like sigma 1 to sigma 2k, because I know that my string is going to be even, right? So so if I'm indexing the letters in my string, I know that the final index is going to be 2k, if of course I'm starting with index 1, right? Okay, so now where does the plot come in? Well, it comes in here, so let's make a plot of the number of A's from sigma um, 0 to j minus the number of B's from sigma 0 to j. So I'm going to make a plot of this difference of number of A's to B's versus the index j, where here I'm using sort of an inclusive index. And I'm starting with the index 0 just to mean that I start from sort of the beginning of the string here. Um, so that when j is 1, I already have a difference of sort of 1. Okay. So what does this mean? Let me just give you a quick example, because this is probably not clear. If I have something like, if I have my string as, okay, this is going to be a long string just because I want to illustrate this well. Okay, so I have my very long string. So the index 0 is going to be sort of the start of the string. So it's not actually going to be a letter. It's going to be right to the left of the first letter in the string. And this is just going to be very convenient when it's going to come the time to plot it. And then these are the indices of the actual letters, right? So you can think of these as J, right? So these are J. And essentially what I'm plotting is I'm plotting, for J 5, right? So for J 5, I'm going to count the number of B's, or sorry, the number of A's from 0 to J inclusive. So in this case, that's 2. So I'm going to do 2, and then I'm going to take the number of B's from 0 to 5 inclusive. So that's going to be 3. And so that's going to give me -1. And so I'm going to plot um, -1 versus the index 5. Okay. So what is this going to look like? 3, 2. Okay. So this is an A minus an B. And then this is J. So this starts at 0, 1, 2, 3, 5, 6. Okay, 14. Okay, excellent. So the reason why I started this index at 0 is because now it kind of makes sense that um, the difference, so it kind of makes sense that NA, the number of A's from sigma 0 to 0, that's 0, right? It's just because I haven't started the string yet, right? So I'm my number of A's is 0, and it's the same thing for my number of B's, right? Because now I'm just counting the number of A's and B's here, okay? So the reason why I wanted to do this is because that means that my plot is going to start at the origin, and it's going to start here. And so now I'm always going to be plotting using this sort of origin as my reference, okay? So again, I'm just explaining to you how this plot works. It shouldn't be super clear how this relates to the grammar yet, because I haven't really explained that. Okay. So how is this going to work, right? Well, now I'm at J1. So at J1, I have 1A and 0 B's. So that means my plot goes like this. Then at J2, I have 2A's, 0 B's. So my plot goes like this. Then I get a B. So now I have 2 minus 1. So I go down. Then I get another B, right? So now I'm here. I'm here. And I have now the number of B's is 2. And the number of A's is 2. So I have 2 minus 2. Right? So now I go back to 0. Right? And so you'll notice this, the origin, right? The y value being 0 in this plot means that I've sort of have the same number of A's and B's for a certain substring, right? Okay. Let me just illustrate this even more, because now if I'm here, right, then what's happened? I have 2 A's and 3 B's, so now I'm at -1. So I go down by 1. Then I get another A, and so then I go up by 1. And so now I've sort of restabilized, right? I've restabilized. I have the same number of A's and B's again. Okay. Then here, so now I'm at 6. So now I got 3 A's in a row. So I go up 3 times. and then I have two B's. So then I just go down twice. Then I get another A and another A. So I go up once, and then I get two more B's. So then I go down twice. Okay. So that means that there are sort of, if you start from left to right and you take sort of um, slices of your string, there are sort of three sub-slices of my string where the number of A's and B's um, is the same, right? Because the number of A's minus the number of B's is 0. So the first slice is here, which corresponds to this crossing of the origin. Then the next time is here, right? So I have this slice, the number of A's and B's are the same. This slice, the number of A's and B's are the same. And then I have this slice, right? So all the way until the end. Here, the number of A's and B's are the same. Okay. So why is this helpful, right? Why is this helpful? Because this kind of tells me that I can subdivide my string into parts where I hit the origin, right? So this can be one part of my string. So if this is the string W, then one part of my string W can be X, another part can be Y, and another part can be Z, where X, Y, and Z, right, each of these subparts, you started, right? So for instance, Z, it started at the origin, right? So it started at the same place as when you sort of started the string at the beginning, right? So it's as if you're sort of reset some kind of clock or some kind of counter, and you're sort of starting from scratch here, right? So now this is like a completely new string where you know that from here to here, you have some number of A's and then some number of B's, and you return back to the origin, right? So that tells me that this section of the string has the same number of A's and B's, right? And it's the same thing for this section and for this section, right? So that means that W can be written as X, Y, Z, where each of these strings, where each of X, Y, Z has NA equal to NB, right? And so I know because my string W is an L, that, it's going to start at the origin because of just how I design things. And it might only touch the origin at the end, right? So it might do this, or it might do this, but it's definitely going to start at the origin, and it's going to end at uh, a value of y is equal to 0, right? Because if at the end of the string, this value is not 0, that means that my total number of A's and my total number of B's aren't the same, right? So if I'm one too low, then I have too many B's. If I'm one too high, then I have one too many A's, right? And so the advantage of this is that it's now telling me what an additional sort of recursive case should be. The additional recursive case should be that I should be able to say, from my start variable S, I'm able to generate substrings, each of these substrings will respect the sort of condition of the language. So that's telling me that I should have a rule that's something like S gives me SS, okay? Why S gives me SS and not, because in this case it was W is XYZ. So someone would have probably expected quite naturally that I should have something like S gives me and then three S's, right? Well, it turns out I can sort of generalize. I can have sort of S gives me any number of S's greater or equal to 2, as long as I have this case, right? So why is this true? Because um, so S gives me SS, right? That gives me, S gives me SS, and then I can replace one of the S's with the same production rule, right? So I can say, I'm going to take this guy and replace it with SS, and this guy is going to stay the same. And so then I can stop. Or I can do this again, right? I could do this again. I could replace this guy again with SS, and then I could get in 3 steps, I can get 4 S's. And then in 5 steps, I could get 5 S's, and so on, right? And so the the advantage of this is that now I'm able to represent any number of sort of values in this graph, right? So if I have something that's very spiky, like something like this, right? Then I can just say, S gives me this S, and then I do the remaining S here. Then I sort of recurse and I do the remaining peaks by using the production rule S gives me SS and so on, right? So this allows me to cover um, uh, the possibility that my string can be subdivided into multiple strings where they have the same number of A's and B's. Okay. And so altogether, right? So altogether, my grammar is going to be, so uh, it's going to have the start variable S, the start variable S, then the single variable S, the terminals AB, and the following production rules. So the production rules P are going to be S gives me the empty string, then ASB, then BSA, and then SS, right? So where, this is the base case, and then this guy is to sort of subdivide into smaller cases that allow me to identify these regions, right? These regions where the number of A's and B's is the same in that sort of smaller subset. And then these guys actually allow me to produce, right? These guys actually allow me to produce, um, so these produce terminals, right? So the way you can kind of visualize generating this string here, right, would be something like, I use S and then I have, this gives me S, then S, then S. And then here I would use S gives me A and then SB. Then I have A and this B here, and then I just use the empty string. Then here I would have something like S gives me B and then A, and then S here would be replaced by the empty string, right? Well, what has to happen here? I have to have an A and then a B. So that's going to be my A and my B here. And then this is going to be the remaining S. And see now, look what's happened. Um, I have sort of um, it's like I have, if this becomes the new sort of x-axis, I get two new places where the number of A's and B's are the same, right? So that means that for this region, right? So for this region, I would need to use something like S gives me S, or sorry, S gives me A, ASB, right? So that would allow me to, let's use a different color. So that would allow me to generate the A here and the B here. And then the S here in the middle would allow me to generate the rest. But to do that, I need to sort of subdivide. So I need to use this rule, right? And then this rule allows me to then do the same thing as before. So then uh, this S here, it's annoying. This S here, I can use, the A and the B and then the A and the B. And then similarly for this S here, I can use A, B. Okay. So you can see I've built up the way to generate this string by combining this sort of way of subdividing the strings with this way of actually producing terminals. Okay. And maybe I think just to illustrate this even better, let me actually derive an actual string. So how would I derive the string W is A, B, B, A, and then B, A, right? So I definitely can't use this production rule from the start because I have something like a mismatch AA here. So instead, I definitely need to start with this production rule. So I have to get S gives me SS. Then it looks like what I have is I have three substrings where each of those substrings had the same number of A's and B's. Namely, here I have 1 and 1, 1 and 1, and here I have 1 and 1. Okay, so that means I need to re-subdivide. So I'll re-subdivide. Okay, and now I can finally start generating, right? So I can generate this this first string here. So that'll be A as B. Then I'll replace this with the empty string. So I'll get AB as S. And then I'm going to skip some steps, but S is going to allow me to derive BA. And then this final S, I'm going to use BA again. Okay. And if you're more visual and you like to see the parse tree, then it would be something like S gives you SS, and could be sort of S again gives you SSS. And then here, you know, skipping some steps, you get AB. Here you get BA. And here you get BA. Okay. And so that's how you sort of design this context-free grammar that generates the language where the number of A's and B's has to be the same for any string in the language. Now, the next thing we're going to do is we're going to sort of prove the correctness of this grammar. Okay, so how am I actually going to prove the correctness of this grammar? So to do that, right, so now to prove correctness. So to prove correctness, I need to do two things, right? I need to first show that the language generated by the grammar is a subset of L, right? And the second thing I need to do is I need to show that the language I care about is a subset of L of G. Okay, so each of these two things can be proved sort of by induction. And typically, you're actually going to need strong induction. Although it's only clear when to use strong induction when you actually sort of start doing the induction and you see that there's a problem with your inductive hypothesis not being strong enough. So it's hard to say when exactly you need to use strong induction versus not. You just have to sort of try the induction sort of first, and then if it seems like you don't have enough base cases, or if it seems like your induction hypothesis is not strong enough, then add more induction, add more base cases to strengthen it. Okay. So how am I going to need to prove these by induction? Prove both of these cases by induction. So for the language generated by a G being a subset of L, what I need to do is I need to show that for every W in the string of terminals such that S can, in any number of steps, generate it, W is in L, right? So this is what I need to show, right? So how can I do this? How can I do this by induction? To do this by induction, I need some natural integer, right? I need a statement that depends on some natural number n, right? That's how the inductions that we're going to be working with have to be stated. So I need to make a sort of statement. So make a statement that depends on some natural number n. Okay. So in this case, what the statement is going to be, right? In this sort of direction, what the statement always really is that so the statement P of n is that every string that can be generated by the grammar G in n number of steps, and you know every string that's a string of terminals has to be in L, right? So the statement is going to be something like if S derives in n steps using the grammar G, the string W, and of course W is a string of terminals, then W is in L. Okay, that's going to be my statement for showing this inclusion. Then the other statement, so let me just give you what the statement should be, and then we'll do the induction. So the other statement here, right? So L subset of LG. In this case, you need to show that every string W and L can be generated by G. So more formally, that every W and L, there exists some sequence of derivations. There exists some sequence of derivations such that S can generate W, right? So the way this induction statement is written is using the length of the string W. So in this case, P of n is going to be if W is an L and the length of W is n, then W is an L of G. So there is this string of derivations that leads to W, right? So why are these statements good enough to proving the correctness of the grammar? Well, remember what induction sort of does is it says, I state that something is correct up till now, and then I show that using that assumption, it's going to be correct in the next step. So for grammars, what does that mean, right? So for like this direction, what does that mean? That means that if I can generate, if everything that my grammar generates within n steps is correct, then I just need to check that in the n plus 1 step, everything will also be correct. And if that's true, then this sort of induction snowballing principle occurs and it becomes true for all n, right? And the same thing in this case, right? That if the string, if any string up to length n can be generated by G, and I show that strings of length n plus 1 can also be generated by G, then I get this sort of induction principle when I get a domino effect and then this becomes true for all n, right? So for any length of the string, it can be generated by the grammar. Okay, so that's why those are the two statements in the sort of proofs of correctness. Now here I'm only going to do this one, okay? Because there's actually already a video where I present how to do this one. So instead, I'll show you how to do this one, and I'll post the link to that video in somewhere in the My Courses tab or whatever. Okay. So let's show by induction that every string in L can be generated by the grammar G. Okay. So how are we going to do this? Well, the first thing we're going to do is we're just going to slightly refine the claim. So refine the claim Pn to reflect the nature of L, right? What do I mean by this? Well, you see here, this statement is for any n, right? But in our case, right, if we look at the definition of L, the definition of L requires you to have the same number of A's and B's. And that just means that W, like we derived here, is going to be of even length. So actually, I don't have to consider every possible n. I only have to consider the n's of even, the natural numbers that are even, right? Because like you don't have to care about strings that are of odd length because they're not in L, right? So So then this principle, like, you don't need to prove that in that case, okay? Um, so then what do I mean by refine the claim? I just mean that let's take into account the fact that the length of W has to always be even. That's just going to simplify things a little bit. Um, so the refined claim is going to be if W is an L and it has length 2n, right? Then it can be generated by the grammar G. Okay. And this is actually going to make the inductive step even easier to actually model. So let's prove this, okay? And in fact, we're going to have to prove this by strong induction. Um, so you'll see why I needed strong induction when I get to the inductive step. But to be honest, for things like this, you have to sort of first try with one base case, and then if it seems like something doesn't really work, then you just go back and you add a base case, and then you sort of broaden your inductive hypothesis. So I'm going to use strong induction on n, and in this case, I'm going to check that my statement is true for two base cases, for the base case where n is 0, and for the base case where n is 1. Okay, so n is 0, that means that the length of W is 2 times 0, so 0. And the only string that's of length 0 is the empty string, right? So then what do I want to show? I want to show that S in any number of production rules can generate the empty string, right? But this is true because I have right, remember the rules of my grammar? In the rules of my grammar, I have as the base case, S gives me the empty string. So I definitely can do that. I want to show this. This is true since S can directly generate the empty string. Okay, so that's good. Now let's test the n equals 1 case. So for n equals 1, that actually means that I'm dealing with strings of length 2 times 1, so 2. And so what are the strings of length 2 that have the same number of A's and B's? Well, those are going to be the strings AB and the string BA, right? So now I just have to check that my grammar is able to generate both of these. I mean, I would be in trouble if it couldn't. So let's make sure it does. So for this first string, I can do something like S gives me ASB, and then I can replace this S with epsilon, so that'll give me AB. And then for the second string, I can use S gives me BSA, and then I replace S with the empty string. So then I get again BA. Okay, so that's great. So that verifies the base case where n equals to 0 and the base case where n equals to 1. So now I can incorporate the fact that I've checked base cases for n equals 0 and 1 in my inductive hypothesis, right? So remember, in strong induction, when you're stating your inductive hypothesis, you're now allowed to say that your statement P of n holds for some range of integers, right? Not just for n. Okay, so that's the advantage of strong induction. So the inductive hypothesis statement is going to be that for some n in set of natural numbers, where n is at least 1, we assume that for every k from 0 to n, right? So I'm starting at n equals n greater or equal to 1 because that was sort of the last integer I checked here, right? And so my inductive hypothesis statement is that for n greater or equal to 1, I assume that for every k from 0 to n, p of k is true, right? So that means that any string of length 2k, where k is between 0 and n, has a valid derivation step starting from S that generates it using my grammar. Okay, that's what the inductive hypothesis is saying. Now, in the inductive step, I need to show that this is true. I need to show that P of n plus 1 is true. Right? Okay. So what is this case P of n plus 1, right? This case P of n plus 1 is, so what I really want to show is that if W is an L and the length of W is 2 times n plus 1, then S, I can generate, using the grammar G, the string W, right? That's what I want to show, okay? So I'm going to use this length of W to my advantage, right? So the length of W being 2 times n plus 1 means that it's 2n plus 2, right? So what does that tell me? That means that W has at least 2 letters, right? And let's sort of explicitly represent that, right? So that means that W has at least 2 letters. It has, its first letter, sigma, and its last letter, gamma, right? And in between sigma and gamma, I have the substring x, okay? Where, x is some substring, okay? So, why is this useful? Why is it useful for me to sort of re-represent W in this way? Well, now the sort of useful ness of this representation is that I can break it down into cases now, right? So now I can use cases. So the first case is, well, suppose that sigma is different from gamma, right? So in other words, that sigma is equal to A and gamma is equal to B, or sigma is equal to B and gamma is equal to A, right? Then what does that tell me, right? Then what does that tell me? So if this is true, then X must be a string in L, right? Why? Why? Because otherwise, right? Otherwise, if X was not in L, imagine it had like a surplus of A's, right? So, X has a surplus of A's. Then I add an A and a B to it. Then the surplus of A's remains, right? Because I've sort of made a contribution, an equal contribution of A and B, right? And then similarly, if I have surplus of B's and sigma is A and gamma is B, then the surplus of B remains. And this is equally true, right? Regardless of um, whether sigma was A or sigma was A and gamma was B, or sigma was B and gamma was A, right? So this holds in both cases, right? So the only important thing is just the fact that I'm saying, well, in this first case, these two letters are different, right? So if these two letters are different, then X, which is a string, right? So X, which is a string of length 2 times n, is in L, right? Well, why is that useful, right? That's useful because now I can use my inductive hypothesis, right? Then X is an L and its length is 2n, right? Then I can use the inductive hypothesis because, why? Because the inductive hypothesis says that P of k is true for 0 to n, right? Well, that's when the length of X is 2n, right? So then by the inductive hypothesis, that tells me that S can generate the string X, right? So that's great, right? Then, why is this helpful? Well, then if sigma is A and gamma is B, then I know exactly how I'm supposed to generate the string sigma x gamma. I can just say, well, um, S gets replaced by ASB, and then S in some number of steps can replace X, right? So it can replace X, but the left and the right, right? The left and the right of this variable remains the same. So I get A on the left and B on the right, but this is just W in this case, right? That's just W in this case. And then it's just similarly, right? Similarly, if sigma is B and gamma is A, okay? So the only difference, right? The only difference is that I have to use a different production rule at the beginning. I use BSA, and then I know that I can replace this A with X, and then this string is actually just W, right? So that sort of shows case one, right? It shows, right? It shows case one of my inductive step. Remember, I'm trying to show that if the length W is an L and its length is 2 times n plus 1, then I can generate it, right, with the grammar G. So to do that, I just said, well, consider an explicit sort of representation of W, where, I have the first letter of W, then the last letter of W, and then some string X in the middle, right? Some string X in the middle. Um, I haven't done anything, like I haven't lost any generality so far. This is just like an explicit representation of the string W for which I want to prove can be generated by S. Then I just say, well, there's this first case where sigma and gamma are different. And in that case, I know in the case that sigma and gamma being different, I know that X is definitely an L and it's of length 2n. So I can use the inductive hypothesis and I know that I can generate it. And then I can just use the fact that I have these other two production rules, right? I have these other two production rules to produce either, AXB or BXN. Okay, so hopefully that's clear. Now, case two, of course, is going to be, well, what if sigma is equal to gamma, right? So if sigma is equal to gamma, right? If sigma is equal to gamma, then that means that X cannot be in L, right? Why? Because if sigma was equal to gamma, so imagine uh, sigma was equal to gamma was equal to A. So I had W is A, X, A, right? Imagine X was an L. If X was an L, then I have the same number of A's and B's. And then W is then two extra A's. Well, that's a problem, right? Because then I have two extra A's. So I have something like N, the number of A's plus 2, but then the number of B's remains the number of A's, right? So then this is no longer the same, right? So I have a surplus, an extra 2 A's in my final string. And that's like a contradiction of my assumption. So that's impossible because I assumed to begin with that W was an L, right? So um, so it can't be that X is an L. So in fact, X cannot be an L. And so what that tells me is that there's no real way to continue using this decomposition to prove my claim by induction. So I need to represent, right? So need to represent W differently. Okay. So how? How? Well, let's just consider, right? So consider the if we think of our sort of plot, right? Our plot that we had drawn at the beginning. So consider the first time that um, the the plot for NA minus NB versus J crosses the X axis. Okay, so imagine, right? So there's two possibilities. it can either cross the x-axis, because it did something like this, right? Or because it did something like this, right? Maybe it did some other stuff here, but this is the first time it crossed the x-axis. And it must have, of course, it must have crossed the x-axis before the end of the string. Otherwise, it would be something like, you had, if it never crossed the x-axis other than here and here, then that means that, I have like an A here and a B here, and then this string, right, this string X is part of L, right? Or if I have something like B and then A here, and I never cross the X-axis ever again, then the plot is always here, right? So then this is the string X, and then X must be in L, okay? So, um, so like the fact that the plot crosses the x-axis earlier than the end of the string, that's a result of the fact that sigma is equal to gamma, right? Um, because of what I sort of just said. Because, if sigma was different than gamma, then it would just be something like this, right? Okay. So now, why is that helpful? Well, now I can represent the string W slightly differently. I can say, well, suppose this was X, and then this was Y, or suppose this was X, and then this was Y, right? So X is sort of the first part of the string, where at some point it's sort of X is the first part of the string W that crosses the X-axis, right? So then W is equal to XY, right? Um, where in this case, the length of X is at least 2, right? And at most 2n, right? So it can't be 2n plus 2 because I'm saying it crosses the x-axis before the end of the string. And it's the same thing for the length of the string y, okay? So why is this helpful, right? Why is the fact that um, X and Y have this range of length helpful? Well, I know, right? I know that X and Y are both in L, right? So because I say, X starts at 0, then it crosses here. So by sort of the principle I was talking about before, I know that the number of A's and B's here is the same, right? And then from here to here, I also know that the number of A's and B's is the same because, I start at an equal number of A's and B's, then I end at an equal number of A's and B's. So, um, so this part of the string is also having an equal amount of A's and B's. Okay. So the length of X is this, and X is an L, and Y is an L, right? So why is this helpful, right? Why is this helpful? Well, now I can use uh, the inductive hypothesis again, right? So by the inductive hypothesis, right? So the inductive hypothesis tells me that if my string is of length uh, is of length 2 times anything from 0 to n, right? So this is definitely between 0 and n. And the string is an L, then it can be generated by the grammar G. So by the inductive hypothesis, S can generate X, and S can generate Y. And by the way, the reason why I had to use strong induction here is because if I had only done, right, so if I only done the base case is n is 0, right, then, I would have sort of proceeded this the same way, and I would have gotten here, but then it would have been very strange because if my base case is n is 0, then it's possible that n is 0 here, in which case I would have the length of X is greater or equal to 2, but less than or equal to 0. And so that's impossible, right? And so that tells me that I need to have, this this right-hand side at least 2. So this has to be at least 2. So that's why I need to do the base case for n is 0 and also for n is 1. Okay. Okay. So the inductive hypothesis tells me this. And why is that helpful? Because now, remember, I have another production rule that tells me that I can, from S, derive the variable S and then the variable S. And then these two things tell me that, this first S can be derived in any number of steps, can be derived to give the string X. And this second S can similarly be derived to give the string Y, and X and Y together are equal to W. Okay, and that shows the second case, right? So just to resume or to summarize, the second case was that sigma was equal to gamma, right? And so that told me that I could no longer represent my string as sigma x gamma, right? So I couldn't use sort of any tricks that I used here. And so instead I had to do something else, right? So if the letter sigma and gamma was the same, then it tells me that, I started with an A and then I ended with an A. Or sorry, no, yeah. I started with an A and I ended with an A, right? So this is having an A and this is having an A. Or I, wait. So I started with an A here and I ended with an A here. Because going up in the graph means having an A. Or I started with a B here and I ended with a B here, right? So if you look at these two graphs, right? If you look at these two graphs, there has to be at least one place where the plot crosses, right? Because if the direction of this plot, like if the gradient is sort of decreasing here and decreasing here, then for these two segments to connect, they must have crossed the x-axis once, right? And the same thing here, right? So these two guys to connect, they must have crossed the x-axis at least once. So then I use that as my advantage, right? I say, well, take the first time that that gets crossed and say that that's the string x, right? The string x has to be an L because, right, to go up on go above the x-axis and then go down to 0, that means that I have an equal number of steps going up and going down, right? So an equal number of A's and B's, right? So that's going to be X the first time I cross. And then the rest of the string, that's going to be Y. So it's possible that my string does, something like this. That's definitely possible. But I know that it's going to sort of start at the origin, or it's going to start at y is equal to 0, and it's going to end at y is equal to 0. So altogether, that means that it went up and it went down the same number of times. So it had the same number of A's and B's. Okay. So that's why I can also say that y is an L. So that's why this is true. And then I just make an argument about the length of x and y, namely that x has to be it has to be non-empty. So it has to have length at least 2 times 1, right? So at least 2. And it has to be at most of length 2n because it can't be the entire string. And then similarly for y. And these two things together, right, under this case, they allow me to use the inductive hypothesis and to use this production. Okay. And that allows me to prove, at least for sort of this direction here, that my grammar is correct. This other direction, I'll just post a video for it. Another video for it. This is also a video. So anyways, I hope that this was helpful. And just in general, this is more or less the strategy that you need to use for the assignment 2 question with the prefixes. So if you use a plot, that's really going to help you. And for the induction, just make sure to know whether or not you need to use strong induction, and make sure that you use the 2 directions, so L subset L of G and vice versa. Okay.